Yeah, you can start.
A very good morning everyone and welcome to our FDP. We are honored to have Dr. Suresh Sundaram sir with us today to share the insights and experience. On behalf of the PCCOE, I would like to extend the warm welcome to Dr. Suresh Sundaram sir and thank them for taking the time to be with us today. Dr. Sundaram sir received the PhD degree from the IISc Bengaluru in 2012. He is a research consultant with the HP Research Lab Bangalore from 2012 to 13. Since 2013, he is with the Department of Electronics and Electrical Engineering IIT Guwhati. He is currently Associate Professor and his research interests include handwriting recognition, biometric and document analysis. So I request HOD Madam to kindly present the token.
Yes. You can come.
Thank you sir, thank you ma'am. So I request sir to proceed with the session.
Just check your email. Yeah. I think I don't need the mic.
Okay.
Okay, I'll just use the mic because I'm having a little bit of back throat actually. Okay. Anyway, thank you for the invitation. Actually, the thing is, I teach the first year students there at 101, that is electronics thing, 1,000 students. So, talking, my throat has, and then there's also change of weather, no? Right, so last week we went to Puja, my wife is from Calcutta. So I went for this Durga Puja, the same Navaratri over there, went into the crowd, okay, and then got the, there's no infection, don't need to worry, it's just an allergy thing, okay. So actually just in short notice I had accepted it, of course, because originally it was supposed to be, yeah, we don't need to get into that, yeah, whatever, right, I mean, so, but I still came because I respect ma'am and just because she asked me, I just, so it's a very, the problem is I've not had sleep also yesterday. I think the flight to Guwahati, you know, no? The timing to Guwahati is overnight flight. You people know or you don't know? So Indigo, there's a flight which directly runs service from here. Okay, from Guwahati it starts at 10:55, reaches at 2 o'clock in the morning. And again tonight I am flying back. So again 2:30 is the departure, reaching there at 5:45. Okay. So the thing is, I have not had good sleep yesterday, actually. Okay, so I'll do my best. Okay, right, and let us see how it proceeds. Okay, so I think what we will do is, if you can tell me your background, it will be helpful because I don't want to do too much theoretical, I mean too much of mathematical also, if that is the case. So all of you teach, some of you teach machine learning or something, or is there anybody new to machine learning over here? You just download both. नहीं वो ये कहाँ पर है डेस्कटॉप पर ओ ठीक है you just download both.
Say downward.
So I have to point it this way. How do I point it? So where should I point for the change of slide?
Yes, the point is there, prepare it and then.
No, just like this. Yeah, so I just wanted to ask you, like, how many of you know what is segmentation actually? No idea. Now I want to make it very So that's what I'm saying, right? So all of you are new to machine learning. Can I expect that?
Yes. Machine learning, image processing.
Image processing.
No, machine learning we know. For image processing, little bit knowledge.
Okay.
So few participants from the mechanical background.
So
it's a
And
mix.
they are just, yeah.
No, that's why I'm asking you actually.
So the FDP is a multidisciplinary approach. So
Yeah.
they are from computer background and they teach machine learning.
Okay.
And they are from mechanical engineering, so they don't know anything about machine learning.
That's what I just want to
It's
ask.
a puff crowd is there. So
Okay, so see, segmentation has a lot of applications. Okay, so let me start with that first. See, let us say I want to do face recognition. Okay, in this room. All right. So what do you see in this room?
Many objects.
Okay. So from my view, I'm taking a photograph. Here. So I will see chairs. I'm seeing the floor. I'm seeing this TV screen. I'm seeing your faces, right? So segmentation is very much dependent on what you want to look at. So essentially, okay, if I want to detect a face, okay, that is also a segmentation only. Rather than saying that I want to segment the faces from the image. And once I segment it out, you can do counting. Are you understanding? Say I want to count the number of people in this room, let us say. Okay? So what do you think I should do? So the chairs, floor, everything should be taken as a case of no, should not be segmented. Whereas what is of interest for me to segment out are the human faces. Are you understanding? That is known as a silhouette actually in the literature. Okay? So that is one way. Yeah, thank you. That is one way. Okay. The other way is, so when you have to do a face recognition, you will have to use a machine learning algorithm, right? And essentially it will be a two-category problem. Why is it two-category? Yeah, face will be one category, non-face will be the other category. So if internet is here, no? Internet works here? Okay. So I will just go to, it's still not loaded anything.
Project the screen.
Oh, okay. So how many of you have seen the cameraman image? Yeah. How many of you have seen the cameraman image? Just click, go to your, I know you're teaching image processing, so you know. Yeah, how many of you have seen the cameraman image?
All. Yes, we have done practice. In FDP only.
In this FTP only?
Yes.
Oh, okay, great. Okay, so what is that image actually about? It is a person with a tripod. You can just check. You can just click, just say cameraman image, that's all, it will come. See, there are a lot of images in machine learning like Lena, cameraman, Barbera, they are very, okay, just look at that. Because what I'm going to explain now is probably going to use how to segment, because I want to make it very simple as I told you, right? So I'll explain some 2-3 algorithms on segmentation, okay? I'll not get into deep learning too much, because the reason is just for, I mean, you people may know, they may not know what is happening, but I'll cover it very simple, okay? Yeah, just look at the cameraman image. So the image is that of a cameraman standing in front of a tripod, okay, with a dome behind him. Are you able to see that? I don't have it here, but
you can see it's again.
yeah, you can just show, ma'am can just show. This is the image. So the problem is I want to segment out the cameraman from the rest of the image, because the cameraman is wearing a dark suit essentially, and the foreground is whatever is there, okay? You understand? So for that, one way to do is what is based on this Fisher discriminant analysis, okay? So what I'm going to explain is something known as Orsu's thresholding or segmentation, which is a very simplistic form of segmentation actually, which you should be able to understand, okay? Because after that you will get the idea what segmentation is. See, segmentation essentially means that every pixel of an image, okay, you are going to take it as a background or a foreground if you are having two categories. So for example, now when we talked about face, I can sit down maybe, right? Because I'm just, yeah, I can sit down and talk, that's better. Then I'll show you the math, okay? So, you can just take one chair, no problem. Okay? Because 5 hours I have to stand. Otherwise.
Yes, yes, no, sir, you feel free.
Yeah, then I can have a discussion, then go to this, okay? Fine. So,
Whenever you feel to take a break also, you may take.
yeah, sure. Now, when you have, see this face recognition I was talking about, okay? Each pixel of your face, see, if I take an image, okay, and let us say I'm having so many faces, right? So each pixel corresponding to a face should be given a label that it is a part of the face. Agree? Okay? And each pixel corresponding to a non-face, such as the floor or the chair or table, whatever, right? That should be given another label, which is so here you are giving the label essentially. Initially the labels are not predetermined. So that is known as unsupervised learning. Okay? So I can use this one. The word, have you heard of unsupervised learning?
Yes.
Okay? So unsupervised learning means, see, you just ask, if you want to ask me, how do you learn a language? This is an example I give to my students also. Okay? How do you learn a language?
Later.
So let's say ABCD, right? This is what we learn in nursery to start with. Okay? Now, you say this is A and this is B, right? And let's say this is A, okay, and this is your L, right? In Marathi, I know this is very different. This is the only symbol I think is different from Hindi. Yes or no? Right? Okay. You know these things because somebody has trained you to, or somebody has supervised you in the form of a teacher to actually tell you that, okay, when you see this is A, if you see this is B. So it is as good as telling that you are giving labels to each of these sounds. Agree? Okay, that is known as supervised. Okay, is it clear? So where you will have labels available to you, okay, and each entity of a class. Okay, see, I want to discriminate between gender here. Okay, here I see the ladies sitting, there the gents are sitting. You know how the genders are different. Definitely all of us know that. Okay, but I have to label, no, using some examples. Okay, these are the ladies. You understand, no? If I want to gender classification, let us say I want to do, let's say, face identification. So I want to identify. Okay, this is madam. This is Deepa madam. Okay, you understand now by looking at her face. So you have to give a label to the faces, but this is given a priori, meaning you have to know the labels. That is known as supervised. When we talk about unsupervised or segmentation, typically the labels are not known. Are you understanding what I am trying to say? Okay, so you have to, that is known as unsupervised learning. Is it okay? So, segmentation is typically an unsupervised learning process. Okay. But segmentation also has the other thing, the supervised setting, wherein I can say, okay, I do a face detection or face recognition. Whichever is marked as a face, I take it separately. Whichever is non-face, it's like a binary thing. Okay. But that is done as a post. So that means I'm still using a supervised framework. And I'm building a classifier to discriminate between face and non-face. Okay, and whichever are face pixels, I am noting them down. Whichever are non-face pixels, I am taking as another label. Is it clear or no? So segmentation typically means what is your interest that you want to pick up. Is it okay? Fine. So what I wanted to tell you is that if you take a image, okay, you have a histogram. Yes or no? So what is the histogram of an image? All of you know what an image is, right? So everybody understood supervised and unsupervised? Supervised means the labels are known a priori. Unsupervised means labels are not known. Okay, generate the labels. Okay, so that is typically what is known as clustering. I want to do segmentation using clustering. So let's say in this room, right, I want to segment the chairs, I want to segment humans, I want to segment the let's say this projector. You understand, right? So you want to learn the underlying objects, okay, and then try to give them a label, okay. Whereas in supervised learning, the labels are already given to you, okay. So once the labels are given, you just train a classifier, okay. Now these days deep learning is used, that you already know, right? So you train a classifier, and whatever of interest is there, okay, so you are looking at a patch, it is getting recognized as something, right? Typically what is done is a bounding box is placed. That's what is also done to segment out, okay. So segmentation has different connotations, that's what I am trying to tell you. It can be done in supervised setting, it can be done in unsupervised setting. But if you are doing it in unsupervised setting, that process is actually called as clustering. Is it okay? Because you want to group pixels based on some similarity. Is it clear to you? Yes. So you can take it either as a classification problem or you can take it as a clustering problem. Used for dimensionality reduction actually is apply this metric of Fisher discriminant, which I will be explaining to you, to an image and then get a segmented output, okay? Understood what I am trying to say? Okay, so I have to go this side, this way, yeah? How do I move this? Oh, okay, I have to just this side now. Okay. Okay, so let us say, this is just to give you an idea, okay? But we are going to apply this concept to an image, okay? Now what I am explaining you is what is called as a dimensionality reduction, but this same idea we will apply to an image to segment a background for the foreground, okay? So how many classes are there? 2 classes, okay? But you don't know what is the background and what is the foreground. So you will have to assign a pixel to a background, assign a pixel to the foreground. Is it okay? Alright. So let us say these are my samples of 2 different classes, okay, and I am projecting them onto a direction, okay, and what you see here is the projected mean, okay, the mean vector after projection, that is far away. That is what you would expect, and also the scatter of these projected points, okay, is minimum. Is it okay? That is what you would expect. See, I will show it to you on the board. See, let's take 2 clusters, okay? I am just putting 2 clusters here, right? So this is one cluster, this is one cluster, meaning these points are there inside, okay? So what I expect is the mean. What is the mean of these 2 clusters? Average. Okay, you have some clusters that, so you have 2 clusters, you have points that belong to each of these clusters. Okay, you want to find out the difference in the mean. Okay, it is a mean vector actually. Why is it a mean vector? Because typically the data will be in D dimension. Okay, I don't know many of you have understood, right? See, we are living in a 3D space, yes or no? Right? But you may have, so let us look at, for example, what are these things? I'll talk about features essentially. Okay? All of you know what features are?
Yes.
For mechanical, you know what is features, no? So you know something called feature vector. essentially. So if you average the pixels, features, vectors, I will get a mean vector. Okay. So I want the difference of mu1 minus mu2 whole square. So what do I expect this to do? Do I want to minimize it or maximize it? Are you sure? Maximize. They should be far apart. Okay. Right? And these points that belong to these each cluster, their spread or what is called as a scatter or variance. What can we say about it? Minimum. So I can say that the sum of the variances also should be minimum. Okay. Now the same idea. So essentially this one. Agree? Of course, this is a very idealistic situation. It may not happen because this will happen only if the two classes are well discriminated or whether you have the segments well discriminated to each other. But typically what is going to happen is there is going to be a lot of overlap between the clusters. Okay? You understand what I am trying to say, right? Okay. But this is what you would hope for. So whenever you do a clustering algorithm, what I would expect is that the distance between, this I am just doing for two clusters, but it is the same idea for all. That is, you want to configure the cluster centroids in such a way, centroids are nothing but the representative of the cluster around which the points are scattered. So I want those vectors, mean vectors or cluster centroids, what we call, okay, to be as far as possible, far away as possible. Understood? Why? Maintaining their, maintaining the, their variance should be as low as possible. Okay. So I will have to maximize the ratio of these two quantities. See, maximizing mu1 minus mu2 the whole square and minimizing sigma 1 square plus sigma 2 square is same as maximizing 1 by sigma 1 square plus sigma 2 square. Is it okay? So this is what is done. Now this particular criterion is what is known as a Fisher criterion. Okay? I am not going to explain this part. I don't want to give the too much math. But this Fisher discriminant analysis is also very important because how many of you know principal component analysis? Right? What is it used for? Right. Fisher discriminant analysis is also used for dimension reduction. So that means you are projecting the data from 2D to 1D. But you are using a cost function there. What is the cost function? The mean of the projected data should be far apart. The scatter of the individual, around the individual mean should be minimum. Same idea you are using for segmentation. And that's why I am trying to tell you. See, you are saying interdisciplinary now, that's why I am bringing that point. The same idea for Fisher discriminant, same cost you can use for segmentation. Now let me tell you how you do this for segmentation. You understood this cost now, no? How you got it? Anyone has doubts? So Fisher discriminant has been used to derive this segmentation algorithm. Understanding what I am trying to say? So the cost is, in both the cases are the same. Here it is used for dimensional reduction, but since this talk is not in dimensional reduction, I am not going to cover that. I will cover for segmentation process. But remember the cost is almost the same. Okay. So how will you do the Fisher, this one? Using Fisher discriminant. So this segmentation which is called as Otsous. Okay. Okay. And this perfect example would be the cameraman image. I don't have the image here because, right, but you have checked already the cameraman image. So what do you think will be, if you go back to the image again, okay, so there's a cameraman here with a tripod. Tripod is in what color? You can just check. Black. The cameraman suit is in what color? You just click on cameraman image, you will see. Okay.
Black.
Black. What about the dome and all that?
White. Grey.
White or grey. So what is your problem statement now? I want to separate the pixels which are from the grid. So that means one I will consider as background, one I will consider as foreground. Now this foreground and background concept is all relative. Okay. So for example, if I am doing face recognition, what do you think will be the foreground? Face. Anything other than the face will be a background. It can be the other way also. But whatever is the positive class or whatever is the positive, you know what is positive class, right? Whatever is the class for which you want to infer, that will be the foreground typically. Is it okay? See, there are other applications I'll tell you. See, our fingerprint is there, no? So one of my students are working on this, palm print. Now, I don't want to detect his fingers. Which is my palm? My palm is this. I want to detect only this. That is also segmentation. Because I want to remove my fingers. Remove means like not take it for analysis, take only the palm region for analysis. So segmentation is very relative. What you want as foreground, what you want as background, you have to define earlier. Okay. So now, so let us say I have an image, okay, and typically images are of what type? They are grayscale, right? And let me consider grayscale right now. Color images also, you know, color images how many channels? RGB, right? And if it's 8-bit grayscale, how many levels will it have? 2 to the power of 8, which is 256 levels, right? 0 to 255. Alright. So what is histogram of an image?
Distribution of all these figures.
Yeah, distribution of all these 255 colors. Now you tell me, for the cameraman image, okay, what should be the, how will the histogram look like? You can just look at the cameraman image and just guess. You can roughly tell. It will be bimodal. It will have two modes, if you see, because there is a significant amount of dark shade, there is a significant amount of white. Okay, but it will not be close to 255. 255 is extremely, the extreme case. It will not be close to 0. I can might as well assume that if I do the, so this has been an assignment, ma'am, which I will send. That is why I am just explaining this so that you can, you want me to send it today? I can do it. There is no problem. I mean, right now, even for the evening lab session, no, they can work it out. Okay? Right? Okay. So, in the lunchtime, I will forward you. Okay? So, what is, yeah, great. Okay, somebody showed this. Okay, so you see this, right? This is dark. So, what is going to be the histogram? Roughly, what is going to be the histogram? It's going to be multimodal, essentially, right? So, it may be something like, I'm just guessing this, okay? Something like this. Agree? Okay. Now my job is to find out what is the threshold. What will be the threshold? That's the segmentation. So, if the pixel is greater than the threshold, it will be, it will be white. It will be yeah. It depends on what you want as foreground or background. So let's assume here that I want to segment out the cameraman along with this tripod. Okay, remember this part will not turn up in the segmentation output. Why? It's a bit white, or it's a bit lighter. So you probably get this, the face of the person, and some parts of these parts will come. You just see, you work it out and see what you will. I'll tell you the output also, what number you should get also I will tell you, so that you can verify. Okay, because this is an assignment we give for our students. That's why I just thought of, is it okay doing it so that people know what's happening. Okay, so now this thing is going to turn up in the background. I want to segment the cameraman from the rest of the image along with the part of his tripod. Now, had this been Alright. So, if the pixel is going to be greater than a threshold, we will say that it is a background. Okay? So, the threshold I have to determine. And if it is less than threshold, it will be the foreground. Okay? So that the cameraman would come into picture. Okay? Don't mark these. I think the earliest picture was fine. No need to, this is interest points I think they are doing. Okay? Fine. Okay? If you see the segmented output, you can just show it. You just see, you can just see that. Okay? Alright. So, okay, I want to use this method. Okay. So how will I write my pseudocode? Anybody? I don't know my threshold initially, right? Or I would assume that any of these 255 levels can be my threshold. Yes or no? Agree? Anybody has doubts? Is it clear? So what we will do, okay, is, where's the, oh, yeah. So let me show this. I'll write the pseudocode here. Okay. Okay. How will I choose the threshold? So I'll have to iterate through all the. See, I have to assume that my threshold is say 0 and evaluate this mu1 minus mu2 whole squared by sigma 1 squared plus sigma 2 squared. So let me now change it a little bit in the formula. Let me say mu of foreground minus mu of background, because the two classes are what? Foreground and background. Okay. Divided by foreground, background. Is it fine? Is it okay? Now, this will be a function of I. And what is I? It will be the iteration essentially. So it is going to be for I equal to 1 to 2. But typically we don't need to go from 1 to 255, 0 to 255. You very well can know it's going to be somewhere here. But just for putting it, I'm just saying it. Okay? 0 to 255, right? Okay. You are going to get a cost which is j of I. For every intensity, if you are going to use, so it's as good as saying, okay, I'm using 0 and separate the foreground and background. I'm going to use the intensity 1 and separate the foreground and background. Understood? Is it clear? Then use pixel intensity 2, use the separate foreground and background. If I'm going to do that, what will be the mean? Now this is 1D. Why is it 1D? Pixel intensities, right? It's not, is it okay? Right? So, mu ft of I, and how do you compute the mu ft of I? So you group all the pixels which are less than that intensity I and take their average. Do you understand? Okay? And then group all the pixels which intensity greater than or equal to I and take their average. All of you know how to take the average, right? Okay? Then what is sigma fg I the whole square? Standard deviation. Once you get the mean, you find out the mean of the foreground pixels take the standard or the variance of the foreground pixels. How do we do that? It's very simple. Okay. You have to take. All of you know now how to take. Can I assume all of you know?
Yes.
Okay, fine. Right. Now, look, I don't want to do two mathematical things, right? Okay. So you evaluate this for every I. Okay. Then what will you do? How many values will you get? How many values of J will you get?
250.
J0, J1, J2? 255. So which one will you choose?
Smallest.
Smallest or maximum?
Maximum.
Maximum. So out of these 256 values that you get, okay, so I will say J of I, max of I, okay, right? Is it clear? In fact, I will say argument max of this. Maximum J of I will just tell you what is the maximum value of J, but argument max will give what? That index. Okay, that will be your threshold. Okay, so then what will you do? Okay, or whatever, depends how you define. Is it okay? So is everybody clear? This is one segmentation algorithm which you should be able to really implement easily. Is there any doubts you have? So I'll give you an overview of some algorithms like this, then we can. Any doubts? Okay, so fine. So the other algorithm which I wanted to talk about, which probably you will know, is known as K-means. Okay? K-means essentially, right? Alright? So, how many centroids will you select over here? K-means.
How many clusters you?
How many clusters? Yeah.
K
K clusters, right? So you will initialize K clusters, okay? So let it be mu1, mu2, uk. Okay, this can be even in d dimensions, need not be a scalar, okay? The earlier case I took it as a scalar to give an example, okay? Typically for color image it will be 3 dimension, for grayscale it will be 1 dimension, okay? Let us say this is in d dimension, okay? Right? Then what will I do? Okay.
Okay, centroids.
Yeah. So as it is the centroids, okay? You will have training samples, right? Okay, which are unlabeled. You want to assign each training sample of feature vector to the nearest centroid. Okay? And then what will you do after that?
Again, recalculate the centroid.
Yes, recalculate the centroid. So let's say for example, there are 1000 points. Okay? See in this 1000 points, 200 points are closer to mu1 when compared to mu2 and mu3. Okay, I want to ask you a question. Now, madam, both the values are sitting close to each other. So, they are the closest neighbors, or you can say their distance is lowest. The people, you understand, right? When I am talking about being assigned, it means in terms of a distance measure. How close they are. Okay? So, that there are some distance measures, okay, which are like Euclidean distance, Manhattan distance, and things like that. Okay? So, can I assume that you people know that you are going to assign the closest center based on a distance criterion. Okay. Now, this mu1 is 200 samples. Let's say for mu2, give me some number, maybe 350. Okay. And for mu k, okay, I'm just taking say 3 clusters right now. Okay. 450 go there. Okay. Let's assume k is 3. Next, what will I do? Yes, amongst these 200 samples are assigned to mu1, you recalculate the new mean. mu1 hat, mu2 hat, mu3 hat. Okay? Then again do the reassignment. So what do you think is going to happen as you keep iterating through? Centers will change and at some point they will start converging. Okay, and the converge, so how would you check for convergence? Yeah, that is one thing. Other way is also to see that, you know, whichever point has been assigned to closest centroid, those points don't change, or those points are at the minimum best. So there is no other swapping that actually happens. Okay. Now, but k-means is going to have a drawback. Okay. So let us say I have data which is like this. Okay. Do you think k-means will work? This is one class. Okay, let me draw it again. Consider circular data. Okay. Do you think k-means will work here? Will I be able to get these two clusters properly? Right. So will it work? Yeah, it will not converge. Agree? Though there are two clusters, I will not be able to converge it, or rather it will keep on going. Okay? Understood? So, in such cases, we do this type of clustering, which is known as DB scan. Okay? How many of you know DB scan? So can you just explain? Little bit at least. Because it's a bit complicated, DB scan. I can tell it to you, but I think I can show a demo, but I think the laptop that's there, no, that is the problem. Otherwise, I could have shown, if the laptop was here, I would have shown the demo straight away.
Can you just
scan, otherwise, No, I just thought if I have internet access, I can just show it directly.
Yes, sir, internet access.
Demonstration. Yeah, let me just put DB scan, then I'll be able to check. No, because the laptop is there, no.
So he wants to show them.
I want to show it from here. No, you said to show illustrations, right? That's the reason why. Why is it kept there?
Actually, this hall has a different facility. They want to record everything from there.
Oh, no, you just put DB scan, just type DB scan.
DB scan. DB scan, sir. Sir, that is a DB scan, sir.
No, this is the first time I'm seeing it's there.
No, you can connect it.
Uh,
They want to talk.
okay, let me just explain it directly here. I'll try to explain it. See, yeah. See, what is going to happen is around a point that you take, you are going to define a radius, okay, of some epsilon. And see the number, and then you are going to have a threshold of the number of points that will be within that radius. Okay? You understand? Now, after that, you will have to identify what are known as core points and non-core points. Okay? You understand what I am trying to say? And then you keep on iterating. So you keep on growing the. So it is a region. Okay, till you encompass the complete cell. So what I am trying to say is, see, you are starting from here. Okay, it will grow like this. Okay. Now the other issue is, understood? This is a basic idea I am telling you. Similarly, you take a point here, it will start it will start growing essentially. Okay. Now one thing about this thing is, it is, see, K-means clustering is always sensitive to outliers. That's also another issue. I'll tell you the reason. Supposing there are points, say here, of a particular cluster, okay, but let's say a point that resembles that is very far away. Okay, what do you think is going to happen? Huh? Yeah, away from the cluster, and also you may have a problem that understood? It is an outlier. Like let's say this point is far away. This guy is an outlier. Say the other point, other cluster is here, other cluster is there. Now just to accommodate this guy, the centroid of this has to change. But is it really worth doing it? It is like this, as a joke I am telling you. You want to pass a student who has failed. Will you change the average of the class? Just for that. You would might as well ignore it, right? You understood? I mean, you are all faculty, that's what I am saying. It's something like that. You will not. So what we will do, we will have to ignore that outlier. So that is done in DB scan. Because what DB scan says is, you look for a region where the density of the pixels or density of the features are more, and include them into the cluster. Okay, and you keep on growing the cluster size depending upon the radius that you are considering and the number of points that fall in. Okay, now the core points are the ones which are a part of the cluster. The non-core points are the ones, or the border points are the ones which are a little bit, you are a little bit vague about it. But then finally you will have to make a decision whether you have to ignore them or put it into the cluster. Is the idea clear or no? Yes. Okay. So yeah. So you can see here. Okay. So this is noisy. Okay. So now, if you want, see, the clusters are all growing. Essentially, you see, this is all are coming into one cluster. Essentially. Now this is an outlier. But let's say if K-means had to be done, this guy has to be assigned to one of the clusters, right? So K-means will assign him to this cluster. But in doing that, what is going to happen? The centroid was here. It is going to shift just for that guy to compensate that. Are you understanding? Okay. So this radius concept essentially will help you to eliminate outliers. Is it clear? So you have to go on putting circular window. You know what is circular window, no? Circular window of some radius, and also check whether certain minimum number of points are there. Okay. So let us say here, okay. See, I have considered a window, and the number of points that I am considering is 4. That means I want at least 4 points to lie within this circle. Alright? So what is going to happen? You will pick up these 4 points, the closest 4 points, right? And the ones that are little bit further away, you put it as a border point, because it is like saying, okay, you are likely to be an outlier, but I still have some, you know, I'll take a decision later. So you keep moving this. So at some point, this guy neighbors. See, let's say you take this as a centroid. Okay? So what, and this is my radius. Same number of points, the radius should not change. You understood? That region, circular window should not change. Number of points should not change. Okay? So though it is a border point, this point still becomes a core point because if you consider the radius, it has 4 neighboring points, out of which some of them are belonging to a core point in the earlier step. Are you understanding or no? So what are you doing? You are starting with 4 core points, let's say. Then each core point you are going to test again. Okay? All the points that fall inside, they are core points. The ones which are non-core points, they will also be tested at one point or the other to verify. Okay. Now you consider the outliers. Okay. Where is the outlier? Outlier is here. Okay. Very far away. Are you getting it? Okay. So this is known as DB scan. Because the idea, so or let us take this. Okay. This is a better good example. See, these points are all close by. Okay. Right? These are all close. In fact, this is a different cluster anyways. This is also a different cluster, which is fine. But what about this point? Are there any points that are... So, if the number of points getting enclosed is 0 around that point, you might as well, it's an outlier. Okay? Are you understanding what I am trying to say? Okay. Now, wherever there is a slight, the points, the closest 4 points, you consider them as core points. The ones which are above that, okay, you consider them as non-core points or border points to start with. Again, you put circles around them. If they enclose a core point of the earlier step, you consider them as core points. Is it okay? Are you understanding what I am saying? So, this is the thing. So, I want minimum number of points for verifying, okay, and EPS is the radius of the circle. Is it okay? That is at the distance of 1 Manhattan distance or Euclidean distance, I am putting a circular region and I am checking the thing. So this is more efficient compared to what? Case. Because what is going to happen is, over here, you start with 4 points, then you are going to enclose each of them again more and more. So if there are any outliers, they will not come into picture. And also, if you have data which is circular and things like that, very irregular clusters, you can say, irregularly cluster shapes, right? Okay, this will work well. See, K-means will not work when your data is circular. Okay, if your data is circularly based, right? You have some data here, this is the one class, and this is the data of the other class. Okay, K-means will not work. Understood why it will not work? There are 2 class clusters, but the issue is these 2 clusters will be grouped as one. Are you getting it? So, but then DB scan will work very well. Okay, so let us say how DB scan will work. Let us say I have. Is it visible? Visible, huh? So let's say I have something like this, right? Okay, I am having all data here and I am having all data here. Okay. So what DB scan will do? It will take this cluster, take particular point, draw a radius, find out the number of points that close to that, the 4 nearest points or whatever it will take as core points, the one beyond that will take as non-core points. In the next iteration they will be converted to core points. Okay. And outliers can also be detected. So let us say, okay, so how is the DB scan going to work? It will start growing. Are you getting it? And how it will work here? See, it will start growing. bangles, no? Just think of bangles or some circular thing, you're just moving it, that's all, as windows, all over the place. Is it okay? Just to give you, like you want to just move it all over, and whichever, all our points which are covered, you take it as one cluster. Now, let us say, I have a point here. What do you think will happen? In between. And let's say I have a point over here. I brought it correctly. What do you think will happen? Will it be considered or not be considered? Not be considered. Because if you consider the same radii around it, if it doesn't encompass a core point. One more thing. Minimum number of core points should be 4. That is also there. Okay, this is understood. Minimum number of core points should be 4. Then only it will work. Okay, sorry. Yeah. Okay. Okay. This is one thing. So is it clear? What I'm trying to say? Okay. The next one is what is called as mean shift. Okay, right? Here I will not cover details because I have deep learning itself is a big topic actually, right? So many of them may not have. So I just show the network, how it is and mind up. But so far you understood, no? Basic stuff at least. Okay, these things people who are teaching image processing. If it's an elective, you may consider adding it into your syllabus. I don't know how many of you teach bag of words or have heard of bag of words. What is it used for? Huh? Yeah, sentiment analysis, object detection. Okay, so that is the simplest algorithm which you can think of based on whatever you have done so far. Okay, so what I want to show you is, okay, maybe I should have got the laptop here. Anyway, doesn't matter. See, all of us have seen an aeroplane, right? All of us have seen a cycle, all of us have seen an auto, okay, right? So what is the difference between these three vehicles? Suppose I want to do vehicle detection. So I can say statements like, aeroplane will have a cockpit, it will have a wings, okay, tail fin, this wing, everything is there. Auto rickshaw will have 3 wheels, okay. And then what is the other one I said? Car, okay. Car will have a dicky, it will have this, okay, the shape of the car and everything, okay. See, there are many ways to do. One is what is called as a Fourier descriptor way, or moments and all that you can generate to actually do shape detection, okay. The other one which is very important is what is known as interest point detection. How many of you have heard of that? Harris corner, and have you heard of it? Okay, maybe you can just type Harris corner over there and just show you. I am using them for the thing. No, it would have been better here only, but anyways.
Actually, laptop is brought, no?
Or SIFT algorithm.
Can it be connected here?
Yesterday it was yes.
SIFT.
Yes.
What is it called? Scale invariant
Feature.
feature transform. Okay. So what are these interest points used for?
Matching of 2 images.
Right. Matching of 2 images, right? That is correct. So, what is done is, you detect these interest points. And what are these interest points typically called? They are called corners. Have you heard of edges and corners?
Yes.
What are edges? Okay, I am talking about edges. Have you heard? Edges are points on an image, pixels on an image where there is a change in intensity. And how do you detect edges? By finding out the gradient. Okay, magnitude of the gradient is large. Yes or no? You consider it as an edge. Okay, and edge has orientation also. All those things we know, right? There is something called as corners or interest points. Okay, right? So interest points are those points which are a subset of an image actually, which, as somebody rightly said, you can use it for matching. Okay. So what is typically done is around an interest point. Okay. I think we have to just use something there. Around an interest point,
To be typed, sir.
you just type interest points. No?
Harris.
Or I think I should give the talk from there. Maybe. And then you put it here. Otherwise, it will be a problem.
Chaudhary, sir.
Or the laptop can be connected here. Then it will be great. I can just type it
That's
off.
what he brought actually.
Oh, okay. So, but it will take some time, no, to get the. Okay, can you just type interest points, please? Interest points. Yeah, Harris corner is also fine. Yeah, Harris corners. HARISCORNER. HARIS. IS, no? IS.
Harris corner.
Okay, let's see what's here. Ah, fine. HARIS. No, IS.
HARIS. Might to be used.
Uh-huh.
Might to be used.
Yeah. Okay. Pick up some corner detection.
Corner detection.
Yeah. Can I be connected?
Sir, is it okay?
Detection. Corner detection.
Okay, let me click on that. This one. Wait. Just click on this. Yeah, just click on this. Yeah, just go down. Right. Okay. Yeah, this is fine. Okay. So, this is a flat region of an image. Flat region means what? It is homogeneous. See, interest points I am not teaching today. I am just explaining what is interest points because finally I am going to relate to k-means over here to get a feature. Okay. So I am just explaining you. You understand? No, I am not teaching interest points here. So we are still on segmentation only. But the main focus right now is how to use these algorithms like k-means clustering and things like that to derive some features. Are you understanding? Okay? Right? Okay. So, this is known as a homogeneous region. Why is it homogeneous? Okay. This is known as an edge. Why is it called as an edge? Okay, there is change in which direction? In one direction or both directions? Are you sure?
No, only one direction.
Yes. There is a change in this direction. There is no change along this direction. Is everybody clear? Okay. What about a corner over here?
Change in both direction.
Change in both direction. You think of a square. Think of a square of 50 by 50. How many corners will it have? How many edges will it have? Edges. Edges means like this. Full. Now let me draw it. 50 by 50 image is there. Okay, size. Square. Okay. My question is, can anybody tell me? 2000? No. Where is it? Ah, here. Okay. Let's say this is an image. Okay. This is a square. Square means as an image I'm talking about. Okay. 50 by 50. 50 pixels here, 50 pixels here within an image. How many corners are there? You're right. 4 corners are there. How many edge points are there?
8.
How many edge points are there? Pixels. How many edge pixels are there? 2500, not 400. 2500. So you have 2500 edge pixels and 4 corners. Which is more compact representation? Understood? See, you can match images pixel by pixel. But wheatish or whatever, right? If you are a fair skin, you will have the fair skin throughout. It is not that one particular pixel of your skin is, you understand? No, that is noise then. If it just toggles like anything, you understand? So our images, or any image if you take, for that matter, they are all correlated. Are you understanding? Like if you have one pixel, a set of pixels, very easily you should be able to, so let's say this is my face, no? So let's say I take a patch. I am very sure what is the neighboring patch going to be, is almost going to be of the same color as this. Agree? There will be some variation of course. Yes or no?
Yes.
But they will be same. So mostly all our images are more or less homogeneous. But there are parts of the image where, like see our eyelid or our eyebrows, okay, compared to the skin, eyebrows are a little bit dark, so that will form an edge. Are you understanding? Our nose. But if you see our nose tip, right, that will be a corner actually. Are you understanding what I am trying to say? Because it's slightly different compared to the rest of the face. You understand, right? Is everybody clear?
Yes.
Okay. Same idea is used here also. So what you do is, instead of an image, okay, you go for, can you just go down, just open the slide show, let's see. There we have some example here. Just open the slideshow. Okay, so there's a very beautiful thing of a horse. I don't know whether it is there. Just go down, it will come. No, this, earlier. No, this one, Harris collar only. Just show an example. Just go down.
No.
Ha. So yeah, you see, yes, okay. So you're seeing two hills, right? Are you able to see some dark red points here? Huh? Those are corners. Wherever the snow is there is best chance of it to be a corner, because snow is uniform. Okay, we have this classroom, right? We have windows. What is important for matching? Is the entire classroom image important for matching, or just the corners of the room? Corners of the room is good enough. Are you understanding? You don't? Okay. Okay, so that is the idea here, essentially. So you are not going to match every pixel, you are going to match only a subset of pixels. Now, I am not going to do matching now. What I am going to do is, I am going to do a descriptor from this. So what I will do is, around each of these feature points, okay, I will take the neighborhood. So that will give you my neighborhood information about that point. Understood? It will give me some information about that point. So let me take a 7 by 7 window about each of the interest points. Okay, now this Harris corner has a problem that it is not scale variant. Sorry, it is scale variant actually. Okay, so for that there is a more advanced version, which is known as SIFT, which is known as scale invariant feature transform. Okay, which is almost similar to this in getting the corners. Okay, but then that can be like it is very robust to scaling effect and things like that. Okay, so just imagine that I have an image and you are running this corner detector algorithm and you are getting the corners. Is it okay? And around each corner I am taking a patch of the image, okay, and I am going to cluster it. Clustering means what? Same, K means clustering. Grouping, yes. Now, how do you think it will be used for object detection? Can anybody tell me? Okay, I'll show you very simple. I'm going to be very childish here. I'm going to show you a photo of an aeroplane. You just put an aeroplane thing. Just type aeroplane, you'll get some plane. Okay. and I'll show you auto rickshaw also. Right? Now you tell me why, how is it going to be used for object detection? Just type aeroplane. Okay. Yeah, aeroplane, you just aeroplane images, yeah, fine. Okay, fine. So you take any of these aeroplanes. Alright, fine. Do you find the same structure in a car? No. Do you find the same structure in an auto rickshaw? No, right? So you consider aeroplane as an object, car as another object. Understood? Auto rickshaw is another called tempo, bus. You understand? What you do is, you apply the corner detector algorithm over the aeroplane image. Understood? So your cockpit will come. So corners will be detected all over, right? A set of points will be detected as corners. You take the region around them and cluster it. Okay? Understood? You take all the objects under consideration essentially. So let's say I'm detecting 4 objects. Okay? That is, what are the 4 objects? Let's say a bus, van, car and aeroplane. I take sample images of each of them, run the corner detector, and around the corner detector I get a neighborhood and I cluster it. Clustering using what? K-means. You can use how many clusters you want. You don't need to have 4. You can have 10, 20 clusters, any number of clusters. Because see, I cannot say that the cockpit has the same cluster as compared to some other thing, right? So I can have even 100 clusters also, no problem. Okay, is it clear? Okay. Now test data comes in. Oh no, sorry, the training data, how will I get the descriptor? What I will do is, I have an image, okay, right? So essentially, this aeroplane itself is going to be divided into 2 parts. The interest points around the cockpit will be different from the interest points about the engine and about the tail fin. Do you agree what I am trying to say? They won't be the same. Yes or no? Agree or no? Because the cockpit is, it's like a nose, right? The structure is different. The structure here is different. The structure of the tail fin is different. Are you understanding what I am trying to say? Okay. So if you cluster them, parts of the aeroplane will be clustered in different regions of the feature space. Are you getting it? Like for example, if I want to recognize a car. So what are the characteristics of the car? Which you can really say it's a car. Say 4 wheels. I want to recognize between an aeroplane and a car. Aeroplane doesn't have wheels, or if the wheels are there but they are very small. And it doesn't have a cockpit. Sorry, aeroplane has a cockpit, whereas your car doesn't have a cockpit. Your car would have that, what do you call? The front part, no, bonnet, which your aeroplane will not have. Yes or no? Then what are the other differences? The dicky also you can say, the 4 wheels, okay. But it's not that all of them belong to the same cluster. Essentially what it means is that the feature points of a car, they have some selected clusters in the feature space, which says that they are part of a car. Understanding? Then the feature points of an aeroplane, they are scattered in the feature space that will indicate that they are a part of an aeroplane. Is it clear to all of you? What I told you. So, what you will do now, you will take an image, find out its interest points, calculate the region or take the region surrounding the interest point, assign it to the nearest cluster. Is it okay? Now typically what will happen is, if you take an image, for an image like this, you will have around 1000 interest points, let's say. I am considering only aeroplane, okay? I am not considering sky. I am considering only aeroplane here, okay? So considering only aeroplane based pixels. Around that I am finding the interest points. Okay. So let us say I have 500 interest points. Now, to which clusters these interest points will mostly fall to? What's your common sense tell you? Will they fall into clusters belonging to parts of a car, or will they belong to clusters parts of an aeroplane? Agree? Yes or no? So essentially this is known as bag of words. Okay? So what we do is pick up the interest points. Apparently you don't know, right? Understood? But if you have training data, as I told you, supervised learning, you will be able to know that this is an aeroplane, so okay, the label will be known. Alright? But you just do the clustering and assign the interest points, the region of the interest points to the nearest clusters. Okay. You count the number of interest points that belong to each cluster. So what will you get? You will get a histogram. Are you understanding what I am saying? Any doubts you have? Yes. You will take the interest points of the car, region around each of the interest points. Do the clusters are already known a priori, right? Assign it to the closest clusters. So you would say that if it is a car, they should be assigned to clusters that resemble more of parts of a car. Agree? So can you do recognition then? Object recognition? Because you would have separated the feature vectors corresponding to. So essentially what we are doing is, you are going to apply k-means first. Okay? Now k is going to be typically large here. K is 100 or 200, okay? So first what you are going to do, you are going to calculate from the training across all samples, okay? Calculate what? Interest points, right? And what is the algorithm you are going to use for calculating interest points? Shift algorithm or Harris corner or whatever, okay? Then what will you do? You pick up a neighborhood around each of the interest points, you cluster them, find out these k centroids. Then for every training sample, you again repeat the process. Clusters are already given to you now, centroids are already given to you. Once you get the interest points in the region around it, that region you assign it to the closest centroid. Keep on doing it for all the interest points. So finally what will you get? And you count the number of key points assigned to a given centroid. So you will get a histogram. So what is the size of the histogram?
Number of interest points.
No, not number of interest points.
Okay.
Yes. It will be the number of clusters. Okay. So you may get like this. Okay. Okay. Alright. So wherever the parts are longer, the bin size having larger number of counts, it is more likely to belong to that particular object. So let's say this I got when I had a car. Now do you think if the aeroplane also will follow the same trend? No. Right? So aeroplane possibly can follow something like this. Understood? I'm just giving some. So you can train a classifier using this feature representation. So this is known as bag of words. And this is very much used. I told you already that segmentation has, you can use segmentation anywhere. You can use it in supervised setting, you can do it in unsupervised setting. Just before the break, I talked about unsupervised. You understand? Where I actually told that the labels are not known and you're using k-means and dbScan, mean shift, okay, to actually learn the clusters or learn the centroids. But now what are we doing? We already have the labels of the objects, which is supervised, but then we are going to use an unsupervised approach in the form of clustering, and then use the cluster centroids to build this histogram and use this as a for feature extraction and thereafter for classification. So this is one way where you can actually use your clustering methods. Okay, now this is not segmentation, but this is related to segmentation. Essentially what I am saying is, I have segmented parts of my object in different regions of the feature space, understood? And then I am asking, given another object, if I want to identify it, I break it into several parts and see where all they fall. And if they fall to a part of a category which is common, I will assign it to that category. Does it make sense? Because see, you know that an aeroplane is the only vehicle which I think has a cockpit. Right? So obviously, if you have a cluster centroid that represents the information that this is a part of the cockpit of a plane, right? So whenever a plane image comes, that particular cluster is going to be voted or binned more number of times as compared to some other vehicle. So did you understand what I am trying to say? Okay, so this is known as bag of words. This is also used actually in linguistics also. This is known as bag of visual words in this case. Why is it called visual words?
Images named as.
Yeah. Okay. Alright. How many of you have heard of quantization in image processing? What is quantization? Huh?
Approximation, rounding off.
Are you sure?
Approximation.
How do you get the quantized levels? There are two types of quantization, no?
Ceiling mark.
One is uniform quantization, other one is non-uniform quantization. Yes or no? Now I'm just giving applications where these things can be, where you may not actually know, but actually it's related, actually, right? So what is non-uniform quantization? Okay, what is uniform quantization? No, I'm just giving applications here, okay?
Step size will be same.
Step size is the same. Yes, step size is the same. Okay, so a histogram is mostly uniform. Okay, what is non-uniform quantization? Unequal step sizes, which is also known as Lloyd-Max. Have you heard of it? Lloyd-Max quantization. Okay. So, Lloyd-Max quantization, if you look at the algorithm, it is same as clustering. How many of you have seen that algorithm and almost same as clustering? What do? You take the histogram, okay, and then you use some threshold values which are like your centroids. You see the pixels which are less than that, you update the mean. You understand what I am trying to say? So you keep on moving the thresholds in a way, okay, so that wherever it stops. It's actually clustering. I don't want to get into it because many of them may not understand. But if you are taught image processing, think of it again. Don't blindly teach the students. Okay, it is related to something which you already know. Okay, I'll just give you a simple example. What I'm trying to say. See, let's say I have some histogram like this. Histogram means histogram of the image. Same thing what we did now, also segmentation, same thing, okay? Now, let us say I want to find 4 decision boundaries, okay? So, let's say 1, 2, 3, 4. Initially, they'll all be equal. But is this optimal? No. Okay? I want the where there is dense, and bin size to be little bit larger when there is less number of pixels. Are you understanding what I am trying to say? Okay. So what I will do is, I will start with like this. Find out the conditioned mean of this, mean of this, mean of this, mean of this, then update. Then again with the new thresholds, find out the points that belong to the closest threshold. Okay? Assign them, again keep updating. So essentially I am moving these are called transition levels actually. Transition and reconstruction levels, you would have heard of that, right? So you keep iterating between the reconstruction and the transition levels in such a way that they will converge. Okay? If you didn't get it, it's okay, but I'm just telling you that if you have thought, next time when you teach quantization, just think about clustering. It is actually clustering only. Nothing more than that. Okay? It is very similar to clustering. Because the way you are going to move these boundaries or these transition levels, okay, they are based on assignment to the nearest centroid. Okay? Is it okay? Is it clear? Alright. Now there is also one more technique. Okay? This I just gave as a sideline. Okay? Because it's not that it's related, but I just thought of telling you. Like the same concept is used. You understood, no? What I'm trying to say, right? It's the same concept is used everywhere in different forms. Actually, though it's not segmentation, same idea is repeating in some ways. Okay, there's another one which is known as VLAD, which also you can introduce to your students because whoever is teaching, who's teaching image processing here? Anybody's teaching? You can raise your hands. I will not say anything. Okay, Deepa ma'am, you can introduce these things because they'll appreciate it. You understand, no, what I'm trying to say? Okay, alright. So, the next one is VLAD, okay. What does VLAD mean? Anybody? So, you have these centroids, no? Okay. You have these samples which correspond, which are assigned to each centroid. Okay. So, it means vector of local aggregated descriptors. Okay, so all the points assigned to a centroid, they are local to that centroid. Understood? Okay, so what is aggregated? You cannot aggregate the points because if you are going to aggregate the points, you are going to get the updated mean. But the residual means you understand, no? The difference between each point to the closest centroid, if you consider and aggregate that also can be used as a descriptor. Okay, so what I'm trying to say is, let's say mu1 is there, and all the points that are assigned to mu1, you take that difference from mu1. Okay, so x minus mu1. And it's not all x, it is only those x which fall in this cluster mu1. Okay, right? And sum it up. Okay, let's say this is j. Points are there. But it's not all the endpoints. You choose only the points such that x belongs to, so xj, something like this.
Excited. Can write excited. I cluster J point.
J point.
UI.
So x, so such that, yeah, j equal to 1 to n, such a way that xj, so it is like if xj doesn't belong to mu I, it is 0. Otherwise, it is accumulated. So where do you think this can be used? This is also another descriptor. Where do you think this can be used? Check it. Is there very This also can be used for object detection. Huh?
Detection.
Detection only. So the algebraic sum of the residuals of the points belonging to a cluster, if you consider, okay, that would actually also be useful. The only problem here is, see, one problem in the bag of words is, there's a problem in the ordering of the feature vector. Because what you're doing, you're assigning the interest point, regional feature descriptor. See, feature descriptor of the interest point can be simple, the pixels around the interest point, okay. You take a 7x7 window, those 49 pixels can be your feature vector for which you are doing. But that is getting assigned to one particular cluster, okay. So essentially this k dimension. So there is no ordering there. Are you able to understand what I am saying? Did you get it? All of you understood what I am saying? There is no ordering over there. My first bin can be the first cluster. Second bin can be the second cluster. Third bin can be the third cluster. Okay, like that. Now in another thing, the first bin can be the fifth cluster. As long as I maintain consistency, you understand? No, there is no ordering over there. Here there is ordering. Because why? Because xj is d dimension, mu a is also d dimension. Are you understanding? So the idea is that certain components in your feature vector, okay, you know what is a component of feature vector, right? Certain, so your feature vector is how many dimension? D dimension. One particular dimension, the differences can be more when compared to another dimension, though they are assigned to the same cluster, and that can be helpful for improving the recognition. Are you understanding? But there is a problem here. What is the issue? Your dimensionality is going to increase like anything, because see, it is d dimension for every cluster, and you are having n cluster, k clusters, so d cross k, so your dimensionality will blow up. But at the same time, you will be able to maintain the order. You understand? No, the order of the ordering of the dimensions, essentially. Okay, so this is another way we can actually use. So what is the baseline in both these methods which I told you? Clustering. Okay, the only difference here is you are using clustering in a supervised framework. That's what I was telling you, right? To actually to get the desired output of recognition. Is it okay? All right. Oh.
So how are obscured images handled? Say some part is not. Say if it is based on the number of wheels we are doing the classification.
Number of
wheels.
bills.
Wheels.
Yeah.
Wheels. 3 wheels. 4 wheels. 2 wheels for a bicycle.
Yeah.
But say the image is obscured and
Yeah.
all the wheels are not visible. So there will be wrong classification. So
Yeah. So those issues are there always, which are called as this one. No. What is that called? Yeah, obscuring, right? They go out of the view.
Yeah.
But still there will be some part. See, as long as there is some part which is discriminative, it will still work. See, there should be at least some part which is there for it to match.
So it has to be a multi-feature.
Yes. Yes.
Multi-feature is
Yes.
necessary here.
Yes.
That is
Okay. There is no occlusion, whatever you are saying. Right? So generally, for example, that's a very important thing, right? See, supposing you are walking and let us say a tree is there, you are walking behind a tree. A part of your body is seen outside, but still you should identify. That's a bit challenging one. But so that's what I'm saying. There should be some overlap, okay, of the region between whatever has been trained to whatever is getting tested. So as long as there is some overlap, it should probably work. Otherwise, we have to do some improvements to it. Actually. Is it okay?
Even distortion can be taken care. Obscure.
What do you mean by distortion? Noise.
No, yeah. Distortion in the image for some reason.
See, distortion can happen in many ways, no? One way of distortion is you can. So, what is distortion you are saying? That's what I want to know. What is the definition of distortion?
So it is still a aeroplane,
Huh.
but I am not saying that about light or scale or not. Neither it's obscure, but the image is bit distorted, or the edges are not clear. I mean, the blur, no, not blurred. The edges are not. Yeah, can be blurred. Yeah, can be blurred.
So then you have to apply a deblurring algorithm
Okay.
to that. So that will become a part of pre-processing.
Deblurring and then
Image enhancement.
Yeah, image enhancement you have to do. Okay. So one of the filters which are used for deep learning is these days even deep learning is used for this deep blurring effect actually. Okay, to remove the other one is haziness also happens actually. Okay, and the other sorts of distortion can also be like foggy day, right? Everything like morning if you see. Here I don't know the fog happens in winter, but at least in Guwhati, morning you cannot see anything. Like it will be like Delhi, na? Very foggy it will be actually. You cannot really see the view. It will be very misty rather. So there all you have to look at some algorithms that will clean up the haze actually. Then we can have to do. But that will not be related to. So that one will affect the feature extraction.
yeah.
That will also affect your clustering
Correct.
method. PhD student. Okay, signature verification is a biometric application. Okay, so what is a biometric? All of you should know what a biometric is, right? So I think all of you know what a biometric is. Okay, so one is iris. Okay, this what do you call fingerprint, iris, signature. Right? And what else we can think of? Ear is also a biometric. Each person's ear. Okay, handwriting is a biometric. Understood? Biometric is same. Okay, speech is also a biometric. The way a person walks. Understood? So essentially, what we are going to do. So all of us are aware of tablet PCs, right? We are using this. That's why I took a case study here. Okay. Wherein there is a tablet, and very often these days when you have to pick up a parcel, okay, you will have to sign on a tablet, right? Of course, he doesn't go verify, that's a different issue. But let us say that you have a system that is going to verify your signature. So what will be the decision it has to be made? Either the signature will be accepted as genuine or it will be rejected as a forgery. Understood? Okay. So, see the traditional methods of authentication include passport, PIN code, okay, and things like that. Okay. But they all require some memory. Yes or no? Suppose you go to an ATM, okay, I think I can come here. Yeah. Maybe you ATM you have to go and click the pin, right? It's a 4-digit number. Okay. So you may forget it or it may be misplaced. You understand what I'm trying to say? So these are not safe and it is stolen also, actually. Right? Many a times we know this ATM frauds actually happen, right? Where people go because 4 digits, so if your luck is good, the forger or the imposter can just come and change the password, and then if he grabs hold of your mobile, you know, they can hack the system. Okay. So there is a problem with these traditional methods. Okay. So now when you look for biometric authentication, actually it is used for improved security. Okay. And yeah. So Iris is physiological because it comes a part of your body. It has nothing to do with the action. Okay, it is about your build-up. Okay, your ears, iris, okay, your face. You understand? Now there are also issues here, like as in the morning somebody was saying, okay, about occlusion, right? Like a person can be occluded a bit, a person can be hidden away, right? Or distorted, whatever, right? Okay. What are the issues with fingerprint? You can stain your hand with ink. Yeah. Okay, or maybe there's an injury, there's a small cut. You understand? So all those issues are also there. Okay. And regarding face, it is very easy. You can mask your eyes, or you can mask your mouth, or you can smile or feel angry. You understand? So emotion detection, everything can come here as a part of physiological biometrics. Is it okay? So there is also work where person is happy, sad, whether looking at the face you want to infer. Okay. So this is the physiological biometrics. Now there is another field which is behavioral biometrics. This is the way we make actions, like the way we walk, the way we talk, okay, or the way we write, okay. The way you understand, right? Something that you gain through experience, essentially. Okay. So here the idea is to recognize a person based on some action. It has nothing to do with the physics of the physiological structure of the body. Is it okay? Got it? Now this one thing. So signature verification, which we are going to deal in this work, is obviously a behavioral thing. Yes or no? This is not physiological. Okay? Because you decide how you want to sign. And you ensure that you sign it that way by practicing. Okay? So signature is one of the traditionally used biometric for authentication of an individual. So what is done in signature verification is, a signature is enrolled. Okay. So you just think of when you are opening a bank account. So what will the bank manager tell you first? He'll give you a slip of paper. Yeah, sample signatures. Now he's not going to, he'll not ask more than 2 or 3. Why is that so? Yeah, the hope is that the signature should remain the same. There can be some variability, but the variability should be minimal. At the same time, he is not going to ask you to give me a fake signature of yours. Understanding what I am trying to say? Is everybody clear? So, your signature is a unique entity, identity, or trait that defines yourself. So that is why, for signature verification, one of the challenges that you will see is that you have to use only training data, okay, of only one user. That is the challenge here. Training data cannot come from another user because it has to be different. So the idea is you have some features of your training signatures which you are storing in a template as a template, okay? And then you are going to contrast or compare the signature of your test data with that of the training and make a decision, okay? If the distance is less, it is genuine. If the distance is more, it is forgery. Is it clear? So essentially this is a one class problem. Is everybody clear? Okay, so that is one challenge over here. It is not multi-class classification, it is only single category. You and your signature defines, okay? And any signature that comes in, if it is resembling closely to your signature in terms of a distance metric, you pass the signature as genuine, otherwise you reject it as forgery. Is it clear? Okay. So, So these are some genuine and forgery signatures. What is shown in red is the forgery and what is shown in black is the genuine of a particular database known as SPC 2004. Of course, these days there are more databases available. There is something called BioSigNet that has actually come up, which has more signatures. Okay. So the idea is you take a set of genuine signatures, okay, and you derive some features out of it, and then you compare the features of the signature against the genuine, and then decide on whether you want to accept it or reject it. Okay. So now, see, this type of signature which we are doing is an online signature verification, wherein actually, so what is the information that you see over here? You have a tablet with a stylus, okay? And what you are recording there is what? Is it an image? No. So what is it? Yeah, it is the trace of the pen or the coordinate trace of the pen. Okay. Now, that's not what it is. You also look at the pressure which a person actually exerts while writing. See, if I ask you to write your signature, some of you may write with less pressure, some of you will write with a little bit more pressure. You understand what I am trying to say? You just put your signature 2-3 times, you will understand these things actually. Okay? Agree or not? Okay. The way you hold your pen also is different. If I ask you, okay, madam, you hold the pen, sir, you hold your pen, okay? If I say, okay, you please hold the way she holds, you will not be able to do it. Have you noticed it? Some people, I see some of my students, no, they are more comfortable writing like this. You understand? Some of them write like this, some of them write, different way. So the way they write the pen, use the pen, the way they tilt the pen, everything is also recorded. Understand what I'm trying to say? So it's not just XY, it is actually pressure, azimuth and inclination. So I explain what these things are. Okay? So, yeah. So let me just come here and show you. So can you just give me a pen, one of you? So I just want to show you the, yeah, you can give me a pen. So let's say I'm writing like this, okay? Now you tell me you write like this, I will not be able to do. And if you say you write the same angle as me, you will not be able to do. Because you will feel comfortable in holding it somewhere. Maybe you will be comfortable holding it here. Maybe some people will be comfortable holding here. You see, the way I move the hand with respect to the pen, that also changed. And the way in which I incline the pen, that also changed. So those are the two angles there. Okay? What is azimuth? So azimuth is the height of your hand with respect to the plane. So if a person is writing like this, that means his azimuth is higher. But versus the pen, let's see, if a person is writing like this, the azimuth is low. Azimuth is the height. That angle. Okay. The other one is the inclination. See, I can write like this. Somebody else may write like this. Somebody else may sign like this. You understand? Now, but then you should next time you sign, you have your own characteristics. It's not that you cannot force somebody to. So now, how do you get the data? So there are many people who have a knack, just like acting, na? Who have a, say, why do actors succeed? Tell me. Can you be an actor today? You cannot. If I say you start crying, you cannot cry at the instant. But you say actors will cry, they will cry. I've seen all these shows, na? Reality shows. I also wonder. Suddenly they see something, tears will start rolling down. Why is it? Because they are talented. They are talented to speak whichever they want. If you want to speak masculine, they can be like. If you want to speak feminine, they can speak like that. Okay. then put somebody's signature and go off, no? Okay? Yes or no? Huh? That it?
Yesterday only one miss was identified.
Yesterday only. Okay. So anyways, what I'm trying to say is that, so the idea is there is some genuine signature, and there are signatures which closely resemble the genuine signature, but which are forged, and which are actually skillfully forged. You understand? So skillfully forged means it has been forged with a lot of practice. Okay? You understand, right? That a person has practiced simply so much that he has learned it that okay, this is the way I can do to copy the. Okay, that's an art. Like how I told you, like artists and all that is an art how they reflect things, right? It's a talent. Okay. So what I want to say is that the attribute of online signature is the information X and Y for here also. The pressure, okay? Yeah. Then inclination and azimuth and pen status. What is pen status? The time you lift the pen up when you are not writing to the time when you lift the pen down for. Is it clear this one? Okay. So now given these things, you are going to record this at every point. Okay? At every instant, you are going to record X, Y, pressure, azimuth, inclination and pen status. So, in any machine learning algorithm, you have to use training data. So what we will do is, for this experiment, we will use two data sets. One is the SPC 2004 and the other is NCYT 100. So you can see the details here. So 40 participants, totally 1,600 signatures. So 20 genuine signature per participant and 20 skilled forgery per participant. Means somebody person has skilled this guy's signature. Okay. So this is a very tough machine learning algorithm because you should try to separate the skilled forgery, which is almost as close to the genuine. Are you understanding? Okay. The other one is NCYT 100. 100 participants, 25 genuine signatures per participant, 25 skilled forgeries per participant, totaling to 5,000. Okay. And for the SPC 2004 data set, the attributes are X, Y, pressure, status, okay, inclination, azimuth, and time. And for the NCYT 100, it's assumed that the time is uniformly sampled. So X, Y, pressure, inclination, azimuth. Pen status is not recorded. So, with regards to features, there are two categories. One is global features, where you can take the length of the trajectory, the maxima, number of maximas, number of minimas, okay, aspect ratio, and things like that. Otherwise, you can use local features, which are around a point, close to the neighborhood of a point. Okay, so something like derivative along x, change in y, okay, change in pressure, change in theta, change in phi. Okay. So this is what is known as online signature verification. Yeah. Now there is also something called as offline signature verification. Offline signature verification is the pen and paper based method. That is, you write on a piece of paper or on a page, you sign, take a photograph or scan it, use the scanned version as a image. So which do you think is better? Online is better or offline is better? So in online I told you X, Y, pressure, azimuth and inclination is available target the stylus. You are going to report the capture of data, and you see the electronic pen which responds to the stylus. All of you see the stylus, no? All these laptops these days have. Then you can eliminate some features like basic attributes or derived features. So typically local features are useful. These days you can use methods like CRS network or LSTM. Have you heard of LSTM? Long short-term memory, okay? Or RNNs, okay? With gated recurrent neurons and things like that. To actually feature, okay? So these networks can be used. Okay, so something like LSTMs or GRUs. Okay. Now regarding the matching modules, okay, there are two ways. One is the distance-based method, other one is the model-based method. So distance-based methods is like, how many of you heard of edit distance? Edit distance. Okay, edit distance, dynamic time ordering. Which of you algorithm you heard? Oh, you have mechanical. Okay, anyways, there are some matching algorithms. Okay, from computer science background, matching algorithms that will match the two sequences. Okay, and these two sequences might be of unequal length. See, because one signature can be from say 0 to 100 or 200 length. This times that. The same signature again will be from 0 to 250. So how many extra points are getting added? 50 more extra points. But you have to match 200 points to 200 points. Okay, I'll give you an example here once I explain what it is. So maybe I'll explain it now, then it will be clearer. I need this one. Yes. See, I want to see the number of changes. Okay. Okay, I'm just going to spell out my name here, write down my name, okay? It's not open, it's to write this. Okay? Let's say I believe in Vastu Shastra. Name change. How many of you have changed your names? Be honest. Nobody? Some name you changed. Okay, great. So after marriage I understand. I'm talking about this one. Oh, that I forgot. But I'm talking about your first name to bring you better luck. You changed. Want to change?
Some people will change.
You want to change or no? Okay, great. Let's say I want to change. No, I'm just explaining this carefully. Yeah? You give me some variation. Let's say SURRESL is better for me. Something. Okay, now I'm not getting into all this thing, but just telling you. Okay, what did I do? I added one extra R. So I included one extra. Right? Rather, just say R went to B. What did I do? Length, yeah, replaced it or substituted. Okay. Remove. So there are three operations. One is insertion, one is deletion, one is substitution. Okay. Now cost of each of them is 1 right now. But let us say that just give me something else. I'm just putting something. Okay, just randomly. So what is happening here? So there is one insertion and one substitution. So there will be a cost for each of these operations. There will be a cost for insertion, there will be a cost for deletion, there will be a cost for substitution. Okay. Now coming back to our example, I told you that the sequence of feature vectors, they are of unequal lengths. Right? let's say x1, x2, x3, let's say x100 is one way, y1, y2, y3. Okay. 105. Okay. 5 more extra. It is not just 5 more. This one. It's not just 5. What can actually happen is x1 will match with x1 because that is fine. x2 can match with x2, or x2 can be, there can be multiple mappings. x2 can be mapped to x2 and x3. Did you understand? Okay, so see, let us say x1 is mapped to x1, x2 is mapped to x2, x3. No, y1, right? Yeah. So what is this? You can say it's like insertion. Okay. Let us say x3 is mapped to y5. So what is happening now? y4 is skipped. It's a deletion. Correct. It's a deletion of. So whatever you are saying, you are adding here and deleting. You understand? So the mapping is not one to one. See, if it was x1 to x100 and y1 to y100, I can say okay, x1 is mapped to y1, x2 mapped to y2, x3 is mapped to y3, x4 is mapped to y4. You understand? So then I will take the distances of those things and then sum up. Understood or no? Now what I am saying, because the sequences are of unequal lengths, certain points will be mapped to multiple points. Okay? So there can be multiple mappings. Okay? Yeah. Okay. All the possibilities can happen. So this is one thing. Okay? One mapping, multiple mappings, or okay. Okay, this is one way, right? Or this way. This also can happen. Understand what I'm trying to say? Yes. So finally, this mapping is going to be one to one. Obviously, if the one sequence is say 110, the other one is going to be 110. Your total length of the mapping that you will do is still going to be 100 because every point has to be mapped. But the mappings can be either one to one or it can be many to one. If it is many to one, it means there is either an insertion or a deletion. Are you understanding? What are you trying to, any doubt you have? Okay, so this possibility is this. Where is the delta? This is insertion. Okay. This possibility can be deletion. Because ideally you would have wanted this to this. Yes or no? Am I right? This would have been mapped to this, this would have been mapped to this, but that's not happening. These two are getting mapped here, and the next point is getting mapped to a point after that. Okay, so this is what it is. Same example, whatever I told you, same thing. But here, this mapping is in terms of what? Feature vectors. So like delta x, delta y, delta p. Okay. So what is delta x? The change in x between pixel, between the points. Okay. What is delta y? Change in y. What is delta p? Change in pressure. What is delta azimuth? Change in azimuth between two successive time taps. Okay. And then you have a series or time series. Temporal information. Okay. And when you are matching this, it is not just all is not one to one because 1-to-1 is not possible here. Why? Because the length of the sequence is what? Unequal. So you will have 1-to-1 mappings, many-to-one mappings, or 1-to-many mappings. So the second case is many-to-one. Okay, see here. This is many-to-one. No, this is 1-to-many, many-to-one, 1-to-one. Okay. So obviously no recursive algorithm. We were just talking about programming now. That's why I thought we'll have to use recursion for this. Yes or no? Okay. So the algorithm which is used for getting it is known as dynamic time algorithm. Okay. And it is used a lot even in speech processing also. Alright. Okay, before I come to that, let me just give you the overall feel of the signature verification problem, which anyways you know. So we have training data. You pass it to a pre-processing block. What does the pre-processing block generally contain? Okay. So you just think about it. There will be noise in pixels, so you have to eliminate the noise, or noisy points rather. How to eliminate? By using median filter or something, you can eliminate, or averaging. Okay. Then you just think about it. How many of you have written on a tablet? Okay. When you actually go and start writing it using a pen, what will happen? Yes, it will slip at that thing. Then you will gain some momentum because that's going to happen however efficient you are. Because the reason is we don't write using a tablet regularly. So the minute you press, because the surface is smooth and the tablet is also a little bit, the stylus tip, right? The minute it starts, it will there will surely be some small set of points which is also noisy, which is known as jitter. Okay. So you have to eliminate that. Okay. So one is noise reduction, other one is jitter. So this is done in the pre-processing block. Okay. And for noise reduction, typically we do median filtering. Alright. Then you go for feature extraction. Because the signature data is given to you, you derive a set of features. Now these days you can derive the features by using a deep neural network. Okay. You can use CNN, depth-wise CNNs. You can use 1D CNN. Okay. Or you can use LSTMs. Okay. Understood? Or GRU. Okay. Okay. You get the features. Then you'll have to match, obviously. Okay. Yes or no? So how will you match? By distance session. So for matching, you can use these matching methods like what have I explained, dynamic time warping or edit distance based methods. Or you can build a classifier which is known as a one-class SVM. Okay, wherein you will have the positive samples as one class, the general as one class, and all other signatures of the other person plus the negative class. But generally the problem what is happening is that you should never train using skill forgery. Why? You should never use the skill forgery at all. Because the main thing is skill forgery is going to and then put a threshold on that. So if the similarity is more, that means that the distance between them is less. If the similarity is less, the distance between them is. Are you understanding what I am trying to say? So you should never use skill forging for training. Because skill forging, I told you, is going to be very similar to the original. Yes. Okay. Because we are doing signature verification. We are not doing signature recognition. If you are doing signature recognition, it is different. Signature recognition means, okay, you are signing, I want to say what is your signature. Your signature will be different from mine. Suppose I sign, I want to say whose signature it is. But signature verification is different. Because there it is more security based. You do not want a signature that looks very closely to yours, getting recognized as genuine and getting into the system. Then there can be serious problem. Now, how do you think the hacking happens these days? Only because of that reason only. People hack the system only because they have credentials and they can do all the mess. Huh? Yes or no? So that's the same thing. Okay. So we should never train using genuine, skill forging. Okay. So that is something to just be aware. So once you match the signatures, okay, you have to compare it against the threshold. Okay. And once you consider a threshold, you will verify it as either as a genuine class or a forgery class. Okay. Okay. So this is known as a distance-based method, where you have methods like dynamic time warping. Okay. The other one is long and edit distance. Okay. There are other methods also. It's known as longest common subsequence (LCSS). Have you heard of it? That is like what is the set of what is the length of sequences that are common, essentially throughout. Okay. But if you teach something on data structures, definitely you would have seen these algorithms coming up. Okay. So I can see you nodding. So LCSS and things like that. Okay. Okay. Now model-based approach is like HMM, hidden Markov models, or support vector machines, okay, and things like that, where you have to train the models, enroll them, okay, and get a similarity score and normalize the scores, right? Okay, and then make a decision and decide whether the signatures to be accepted or this one as it works smoothly. Okay. So what are the possible errors that can happen? It's a binary classifier, so only two types of errors can happen. A genuine signature can go as forgery, or a forgery can get accepted as. Now, this is something very important. Which of these errors are tolerable?
Genuine doing function.
Yes. Okay. I'll give another example. So COVID is a big disaster for us. It's not everyone, right? Now, a person has symptoms, system is saying he's not COVID, and let's say he had comorbidities. You know what happened to many of them, right? Many of them lost their life or went to hospitalization, things like that. But let's say a person is healthy, but since system is still saying he's positive, there is no problem at all. So in a similar way, this is the thing. Okay, so a person, a genuine signature, going as a forgery is okay, whereas the other decision you have to bring it as low as possible. So that is the most important key in any biometric system, where it is a accept or reject. Why is it that if you have seen, right, if you lost a password or something, right, it says okay, give you only 3 attempts, 2 attempts. Why is it? It's because of this reason. You got it right? What I'm trying to say. You would have seen that if you lose password or something, in many of the things it says, okay, you please. It's a very sensitive stuff, like bank details and things like that. Just don't try it out, but then let's say you forgot your password or you accidentally put some other password, it will always say, okay, it will be locked after 3 attempts, 2 attempts, then go to the bank and check. I think all of us have seen that message now. Why is it happening? This is the reason. Because it doesn't want a person who is actually stealing something and get the credentials here. It wants to enter the genuine party. Okay. So likewise, that has to be weighted out. Like a signature which is false acceptance rate is percentage of forgeries that get access to the system. And equal error rate is the particular case where FAR and FRR are the same. So you plot FAR and FRR in your two-dimensional plot, and for every threshold that you set, you will find out what is the FAR and FRR. So maybe I'll explain this on the board. Okay. So let's say you have done some algorithm and you have decided on a threshold. Okay. This is not segmentation. Okay. This is to get the lowest error. Okay. So let us take the duster. How many of you know ROC curves? Something similar. You teach machine learning here? Because you're nodding your head for everything. How do you know? You're working in this area or what? You heard of it? Okay, good. Fine. So, no, she's nodding for everything, so that it's not okay, she can come and teach. Huh? Oh, you're, which one? You're faculty or? Okay. Oh, PhD. Okay. Alright, so you may see here, for a given threshold, you compute the FAR and FRR. Vary the threshold. See, by varying the threshold, what is going to happen? FAR and FRR both are going to vary. That variation you plot for every threshold. So let's say for this particular value of FAR, that's for one given threshold. This is for another threshold. This is for another threshold, another threshold, another threshold, okay? Then you draw a line which is at 45 degrees. Why? Because I want the error rate to be equal to where that point where FAR and FRR are same. That will be 45 degrees line. Yes or no? Intersecting with what? This curve. Okay. So this particular value will give equal error rate. Now let us say this is one algorithm. Okay. Now if I want a better algorithm, how should it be? I should get a curve which is something like this. A much better algorithm. Clear? So this is what it is. Any doubts you have? Go. So one thing is, we are talking about DTW system right now. Okay. So the traditional DTW system, okay, uses only the DTW scores for making the decision. Okay. So okay, let me first explain what is DTW, the algorithm, then it will be easier, I think. So this is the DTW algorithm. Okay. So what type of an algorithm is it? It is recursive in nature. Okay. So again I have to use the board. So I'll just show you. Okay. So what you do is, you have two signatures. Okay? That needs to be matched temporarily. Okay? You want the starting is point here and the ending should be here. Okay? Means the first point should be mapped to the first point, last point should be mapped to the, they are called boundary conditions, beginning and ending conditions. Okay? In between, how many possible paths are there to reach your destination? I want to start from here and end here. So how many possible paths are there? There are many. I can go like this. I can go like this. I can go somewhat. You got it, right? Understood or no? I want to choose that path for which if I consider the mappings, so let's say the mappings are something like this. The overall cost, if I accumulate along wherever these matchings have happened, that is what. Is everybody clear or is somebody having a doubt? See, the first axis is one signature, the other axis is another signature. You have to start from 1, 1. You have to end at n, n. Let's say n is the length of one signature, n is the length of the other signature. Length is right from the timestamp. Okay. You have multiple paths to reach. Yes or no? But I want to choose that particular path, allowing, see, definitely if m and n are not the same, see, let's say you have 100 sample points and 110 sample points. Definitely, or it will not be 1 to 1. Yes or no? 1 to 1 will happen only if m is equal to n. The first one gets matched first one, second one, second, third. But when the unequal lengths come, some points will have to be skipped. Agree or no? You just think, I have a sibling of 100 points. I want to match it to even 102 points. So you will see that you may have to compromise. You will have your very high chance of having many to one or one to many mappings. Okay? It is not just substitution, essentially. It is more than that. You may have insertions and deletions. Okay. So, there you go.
What is time considered in that?
What?
While matching the signatures. Why is the temporal matching or the timestamp considered for the
It has to be considered, no, because you are citing in a particular sequence, okay?
So in the digital signature we can record the trace, the part.
Yeah, that's what is happening.
and time
Yes.
for that.
Yes.
But the sample that we have, in that
There are also
we have
traces.
time.
There also time is.
That is also digital signature
Yeah.
recorded,
Yes.
and that is matched with
Yes.
the live signature.
Yes.
The test signature.
Yes.
Timing.
So all of the timing information is good.
So trace whether it is identical.
Yes. Correct. Understood? Okay. So let us say that this is the type of mapping which is allowed, which is the most, which gives the minimum cost. Okay. So that means I accumulate all these scores and I will get the total cost. Okay. This is a path, right? Yes or no? This is known as warping path. Okay. Is it clear? So earlier works, what they did is they just considered the overall score. They just accumulated the scores around the warping path and considered that for verification. But what my student did as part of his PhD work was this characteristic of the warping path. He tried to get another score. Understood? And then try to combine this with the original DTW score to improve the or the input to reduce the what is that equivalence. Is it okay? Okay. So I don't want to do the math, but to get that graph, okay, which one to get this working path, okay, you will have to use this algorithm, which is recursive. So let's assume that the working path is now determined after applying the algorithm. So the working path mappings are A1, B1, A2, B2. This A1 is one point of one signature, B1 is other point of the other signature. Say 1, 1, 1, 2, 2, 3, means what? First point is matched to first point, this point, second point. Got it? Huh? Some idea you got? Just that matching. Okay. Alright. Okay, so let me just show you the features that we are using. So the features we are using are first order differences, right? Then sine and cosine measures the angle of at every point with respect to the horizontal. Second order differences, length based features. So in total you are having around 12, I think. 5, 6, 7, 8, 9, 11 features. 11 features you have in here. So this is at every point, mind you. Okay. Now there is a factor called R over here, which is a spacing parameter. See, this is the derivative not with respect to the next point, but with respect to a point that is R spacing away. See, this one helps to actually reduce the noise in a way. Understood? So it removes the noisy signals essentially. So you can use this method, okay, to get the derivatives, not between consecutive samples, but between sample points that are spaced R points away. Okay? Alright? So we also experimented what are the resulting features if you use different values of R. So here, if you consider genuine signature, it can be some one. With R equal to 1, and let's say for R equal to 6, okay, this R equal to 6, R equal to 1, genuine, what calculation can you make? What calculation can you make? Figures that you see in the below. General signature R equal to 6 and OD signatures R equal to 6. So where do you think the figures look different? The top panel or the bottom panel? Huh? So what is your conclusion? R should be? Yes. So if you take the derivative with higher values of R, okay, the discriminability between the genuine and the skilled forger, okay, mind you, these are all skilled forgers, they are not okay. So you are able to discriminate, okay. Alright. You are getting the warping path score, you are taking the normalized DTW score, fusing both together, getting a combined score and using it for verification. See, earlier works didn't use warping path score. Okay, they just used the DTW score only for verification. Whereas in this work, okay, we are using the warping path score. Is it clear? Okay. So, and what is the decision again? Genuine or forged. So now I'll give you an example. Okay. Okay. I want to skip all these things. Okay. See, essentially what we are doing here is how many of you know correlation matching? Correlation matching, that is you have a segment and you want to match it with the closest segment with the other segment. Okay. Correlation is something to difference. So there's use an image processing also. So what you do is you take a patch, a set of points are there. It's nothing but something like a mean squared error or squared error difference. So here you're taking the average sum of the average sums. Okay, there's L1 distance. Right. So what you will do here is, let me forget this equation right now. See, there is a segment between 3, 4, 5 in the test signature T, and you want to find the closest test segment from the time samples of the training set. So there is a training signature, there is a reference signature. You are taking a window size of 3 in the test signature and finding out which window size or which size of set size 3 from the training signature which matches its best. So what I will do is, I will take this, match with 1, 2, 3. I will take this, match with 2, 3, 4. Take this, match with 3, 4, 5. So I will get so many scores, right? I will check the one that is the minimum distance and I will keep a track of it. Okay. Likewise, I will move it again. I'll move this again and find out. So I'm doing another type of matching. What is that matching? Based on correlation. Already you have done one type of matching and found the warping path. What is that? Using dynamic time warping. You utilize these two matching trend and then decide. So if you have understood it, what should be your conclusion? Between correlation match and dynamic time warping match, can you conclude on something? Tell me, just think and tell me. There's a warping path, there's a match due to that. There is a match due to these correlation matches. So when I'm comparing genuine to genuine signature, between these two matches, should they be far away or should they be close by? Yes, that's all. That is the idea. So one you have got from the warping path, the other one is you are getting this correlation match. And you are matching, you are finding out the difference between the match that you obtain on the dynamic time warping path versus the matches that you obtain from this correlation score, and then deciding whether they are far away or close by. Okay, and use that to develop a score and then combine it with the original DTW score to, okay, that part I'll show you. So what we are seeing is this. Okay, I'm just doing the illustration. Forget about example, Magda. It's very complicated sometimes. Because notation is everything I don't want to cover. Okay. Now this is genuine, forgery to agree. But you see what's happening. I don't know whether it's visible. This is okay. This is 0.70. Genuine to genuine. Okay. And forgery to genuine is 0.65. So is there a problem here? Misclassification is happening naturally. Yes or no? Genuine to genuine score is higher than genuine to forgery. Okay. Now you analyze the warping path. Okay. And you also analyze the matches around the warping path with the matches that you obtain from correlation. That is, I took segments of length 3 and matched the points. What do I see between this figure and this figure? This is genuine to genuine, this is genuine to forgery. Think about these red points. The red points are the matches with the correlation. The points which are lying on the blue line, they are the matches due to dynamic time warping. So if you look at this figure, the matching due to dynamic time warping and correlation matching are all along the warping path more or less. Yes? There are less outside, whereas here there are more. So you quantify the distance of how far the matches are in terms of in terms of the timestamps. Okay, and then come up with a score, and then use that score and add it to this. So now you see what is D1 plus D2, and what is D1 plus D2 here? Which is better? Earlier we said D1 score is higher here, D1 score is lower here, and classification will go wrong. Now I am taking D1 plus D2. Now are you able to convince yourself? I am not able to see the numbers. See, D1 for genuine to genuine is 0.70, D2 is 0.06, genuine to genuine. So what is D1 plus D2? 0.76, 0.76. Forgery to genuine. So I'll tell you the numbers: 0.65, 0.20. D1 is 0.65, D2 is 0.2, 0.85. If you add up D1 plus D2, is it okay now? D1 plus D2 is 0.85, is higher for genuine to forgery match as compared to 0.76 for genuine to genuine.